Hi everybody. I think this is week 5 or 6. I think it's week 6. I don't think we've done 2 rounds of biology, 2 rounds of chemistry, 2 rounds of physics. So we're going to look at some physics principles today, very maths based, but relatively light on the content, so we have a nice easy break week this week. Well, if you're a maths brain, it's easy, I guess. Content light, maths heavy. So, going to look at the conservation of energy. So we have your energy, you're doing work, and then you put that work into the cart, and the energy does work. So energy, without being utilized, is useless. It's just energy. So we have this concept called the law of conservation of energy. Basically says that energy cannot be created nor destroyed. All of the energy that was here, beginning of the universe, is here now. So what you put in is what you get out. But the total amount of energy is conserved. But the energy can be transferred. So whilst the total energy that you started with is the total energy in a system that you finish with, it's not in the mode that it started in. So we have thermal energy in the form of heat that can create steam, which creates mechanical or kinetic energy, which then creates electricity. And what we call that is the total amount of energy is conserved. It doesn't change, it's just converted from one form into another. So from chemical energy in the foods that we eat, eventually is broken down into sugar, which is reacted with oxygen to form ATP, and then we get motion. But the total amount of chemical energy we started with is significantly less than the energy of motion through riding the bike. The energy from the sun, the plants use the energy from the sun, the light energy, to produce chemical energy, and they do that by producing sugar through photosynthesis. So let's go straight into the whiteboard tonight. Why not? So we burn fuel to go from chemical energy to motion, the energy of motion. So we have hydrocarbon, so this is our fuel. Don't worry too much about what it is. But in each of these bonds, there is a certain amount of chemical energy. So let's say 1,000 joules of energy here, which is not very much. But if we then combust it, so we set it on fire to break all these bonds, which releases energy, it goes to the crank in the engine, to the drive shafts, or to the differentials. Could have this mixed up, but to the drive shafts, tires, to the road. And in every single step here, we're losing energy. So in this process of combustion, the piston is moved upwards to spin the crank. So we're going to lose some energy to friction. The crank to the differentials again, so friction when we lose. Friction is heat energy. The differentials to the drive shafts, because it's a spinning, two things spinning against each other, we lose friction or lose heat as friction. Again, by the time it gets to the road, there's only about 300 joules left. 300 joules, or 30% of the energy that was originally in the fuel actually makes it to the road. So each step, we're losing heat. But this energy doesn't just disappear. It just goes from kinetic, so the energy of moving objects, to heat. It changes form. It's still there. That 1,000 joules of energy that we started with is still floating around the car. It's just not going through this process anymore. Only 300 joules of it are left. So if we look at practical examples, so this gasoline converts chemical and potential stored energy converts this chemical energy into kinetic energy. So a battery does the same thing, takes chemical energy. Excuse me, I have to go let my wife in the house because apparently she doesn't know how to unlock the door. So battery stores the chemical energy within the battery. To electrical energy. If we have a dam, so a hydroelectric dam, converts the kinetic energy to electrical energy. So I'm going to give you 2 minutes to have a look at this and think what other examples there are. So another couple of examples you can think of, just write them down. So write down any other examples where you have energy conversion. So, am I still recording? Yeah, that's right. Again, think about ecology that we talked about. So, I've got about a million different presentations chopped up into one here. So, we have the chemical energy in the fuel, to the heat energy when we set it on fire, to mechanical energy, so the steam spins the turbine, creates electrical. So we have the law of conservation of energy. This is just the actual law itself, which is energy cannot be created or destroyed. It may be transformed one form or another, but the total amount of energy never changes. So Matilda's just joined us. I'm Matilda. So everything has a potential energy, which is based on the mass of an object. And we can look at that in gravity. So the potential energy, there we go, there's one another pen gone, equals mass times gravity times height. So if I'm holding a ball 2 meters above the ground, the mass of the ball is 100 grams. Gravity is 9.8 meters. And we'll go over gravity later on. Times the height, which is 2 meters. And that's how we determine the potential energy of something. Kinetic energy is the energy of an object at motion. The equation for this, energy kinetic equals half mass and speed, or velocity. Again, something we'll go over later. So it's half times its mass times velocity squared is how we would work out the kinetic energy of something. So the energy of a moving object. So again, we're looking at mechanical energy here. So the transfer of energy and how much energy is lost. So up here, and our awesome little car. So here we have high potential energy. Down here, we have minimal potential. So the potential energy here is really low, whereas here it's low as well, but it's not quite as low as it was here. So the total, and up here we have low kinetic energy because it's just starting at the top of the hill. Down here we have maximum kinetic energy, and here we have high kinetic energy because it's still going. So it's picking up speed, and it slows down a little bit, and the potential energy is going to take it over the top of the hill. So I won't go through another one of that. So speed, distance, and time. What is the relationship between these three? Any ideas on that? Just write down your thoughts on what the relationship between speed, distance, and time is. So speed is the distance traveled over time. Gonna turn off my equals distance over time. So the distance may be 100 kilometers, and the time might be 1 hour. So how many kilometers? What do you think our speed is? So the speed would be 100 kilometers per hour. So it's how far you can travel in a certain time. So if you're traveling at 100 kilometers an hour, then you can travel at 100 kilometers in an hour. So this is the average speed. And we have this SDT triangle. So and we can determine one of these numbers if we know the other two. So train travels 120 miles in 2 hours. What is its speed? So if we don't know the speed, then we would just do distance over time. So 120 divided by 2, 60 miles per hour. So now we want the distance. So, any ideas how we would get the distance? Don't say them, just write them down. So, distance, speed times time. So, 8, they ran for 25 seconds. For each of those 25 seconds, they ran 8 meters. So it would be 8 times 25, or 200. Again, same thing, we must give the units. So, again, you can tell us teaching over in the UK, a lorry leaves Stoke, travels 150 kilometers to Leeds, an average of 60 kilometers per hour. How long did the journey take? So now we have time. So that would be distance over speed. So 150 divided by 60. Or the total number of kilometers divided by 60. Should give 2.5 hours. Again, we have to use the units. Again, I'm not going to go through this again, you guys. Smart enough, I think. Don't need to go over it twice. So, density, mass, and volume. 3 very important measurements. And this is not just physics, this is physics, chemistry, and biology are used. So density equals the mass divided by the volume. So how much it weighs versus how much space it takes up. So the weight of a given amount of material. So now we have another handy little triangle, DMV triangle. So we cover up what we want. So density is mass over volume. We know that already because we saw that. What about mass? Mass be D times V, although that hasn't gone to the right spot. Mass is D times V. So what happens when I chop and change these presentations together? They never quite come together the way I want them. What about volume? I'm going to let you guys figure this one out. I'll give you a minute to figure it out. So volume would be what? Take away the V. Volume equals mass over density. Why is that still going off? I've turned the Facebook notifications off. So let's put this into, got your pen and paper. Steel girder weighs 2,500 kilograms and has a volume (100 meters cubed). What is the density? So we know, if we look do a little so we know the mass, we don't know D. So will we do M over V, or mass over volume? Because we already know the other two, but we don't know density. So 2,500 divided by 100, 25. And because we've had kilograms and meters squared, the question would need to read 2,500 divided by 100 meters cubed, which would give us 25 kilograms of mass per 25 kilograms of mass per meters cubed. Again, we have to give the units. Okay. It's gone. Speed, velocity, acceleration, and Newton. So we learned about the Newton's laws and how it works with the different forces. And now we can apply some of that to the velocity, acceleration, speed, and Newton. So velocity So, velocity is a strange one. It's what we call a vector. It has both magnitude, or the speed, and the direction. So this is getting up to sort of 10, 11 maths and science now. So the vector has a magnitude, or the speed, as well as a declaration. So, just said that word again. Thank you, Walla family, for making me very self-conscious of that. Okay. Acceleration is a change in speed. It is not speed in itself. Definitely starts with 2 L's now. But gravity is accelerating you down to the ground at 9.8 meters per second per second. or meters per second squared. So at 1 meter, you're doing 9.8. 2 meters, you're doing 17.6. 3 meters, 27.4, so on and so forth. So it's a change in the speed. Can also be change in direction. So acceleration of A equals a change in velocity or speed over an elapsed time. So gravity, for every 9.8, every meter you fall, from a height, you increase in speed at 9.8 meters per second. Pick up speed. So, change in velocity over elapsed time. So, if we look at my very creative drawing, 0 to 100 kilometers in 3 seconds. So the change in velocity is from 0 to 100. So the change in velocity would be 100 kilometers per hour over 3 seconds. What would that equal? 33.33333. I'm just going to call it 33. So, acceleration and speed are different. Acceleration is the change in velocity. So speeding up from 20 to 40 is accelerating. So you're changing the velocity of the car. So the acceleration of a car that accelerates to 0 to 100 kilometers an hour is 33 kilometers per hour per second. I don't think that little car there could achieve those kind of speeds, but you know. So we can take that further if we wanted to, down to 9.1 meters per second. But I wouldn't worry. 33 kilometers per hour per second is as simple as you'll need to take it. So here is where that gets a little bit muddled. We have what's called free fall. Acceleration. So we know the acceleration is change in velocity over the elapsed time, despite what that slide now says. And when we're free falling, it's 9.8 meters per second per second. And we have this, everything has a maximum free fall speed. That's determined by surface area, by the clothes you're wearing, by the wind on that day, but is called the terminal velocity. Terminal velocity. So everything will eventually get, humans, I can't remember the max speed, but in an atmosphere, gravity is not the only thing that affects
a free fall. So if I drop a bowling ball and a leaf in the atmosphere because of wind resistance, because of various other things, the bowling ball will hit the ground first. But if I take all of the air out, they hit the ground at exactly the same time, when they're dropped at the same time. There's a video on YouTube. Brian Cox does this experiment where they take a bowling ball and feathers into a vacuum, and you actually see them falling at the same speed, despite the fact this is thousands of times heavier than the feathers. So, lucky last slide, I think. Mass and weight. So, the kilogram is not a unit of, it's not a unit of force, it's a unit of mass. So it weighs how much stuff. When you are standing on the scales, they have a spring. And it's not how much of you is pushing down into the ground that weighs, it's how much force is pushing back up. So we know if we have 85 kilos, we times it by 9.8 meters per second squared, which is the acceleration force of gravity that we just spoke about. We get a force of 833 newtons. Oh, I think the number, if you go to the moon, I think you weigh about 1/6 of what you do on Earth, because this is 1/6 of the gravitational force. So this is your actual weight. If you weigh 85 kilos, your weight is actually 833 newtons, not 85 kilos. Okay. Thanks, everybody. I don't even know what the time is. Oh, not too bad.